Hey folks, we're going to continue talking about electric flux, and this will lead us into Gauss's law. So I've written the two equations that we've already discussed in the previous sections. The second one is the more general version for electric flux. That's the more useful one if you have a non-constant field. If you have a constant field, you can certainly use the top version there, but the bottom version always works. So here's my next thing for you to consider. Let's say I have a positive charge, and that makes an electric field. And I asked you to draw the electric field. Well, you would hopefully draw a bunch of field lines outward, right? Because if I put another positive charge near this first one, the second positive charge will be repelled by the first one. So that's what the electric field lines represent. Now, let's say I were to enclose this charge with two different spherical surfaces. Let's say there's the first one, we'll call that S1, and here's the second one, we'll call that S2, okay? And I'm going to ask you a couple of questions here. The first question is, where is the electric field stronger, surface 1 or surface 2? Well, hopefully you would say surface 1, because the field lines are closer together at surface 1 than they are at surface 2. Also, you're farther away from the charge, so the field is less. The electric field equals KQ over R squared. Well, R is bigger, so E is smaller. But here's the next question. Through which surface, S1 or S2, is the electric flux greater? Well, at surface 2, there's a less strong field, a smaller field, but there's a greater area, right? So which one's more important here? Well, remember what electric flux is. It's simply the number of field lines leaving or passing through an area. Well, if you look, I've drawn a total of 8 field lines. All 8 field lines pass through surface 1 and surface 2. So it turns out that the electric flux is exactly the same for surface 1 and surface 2. Now, if you were going to calculate the electric flux, here's what you would do. Okay, you would have your equation. You would do a double integral because it's a surface, but now you'd put this loop around or in your integral, and you would write E dot dA. Okay, now what does that loop mean? Well, that has a very important meaning. That means a closed surface. That means that that surface encloses a volume and there's no breaks in the surface. So a sphere would work, any shape, three-dimensional shape would work. A cube, rectangular, solid, whatever. But now you have an enclosed volume. You're surrounding a volume with a surface. Okay, so when you see that symbol on a double integral sign, that means a closed surface. Okay, and in this case, if I were to write the electric flux for 1, it's going to equal the electric flux through surface 2. And I'm not doing any values or anything here. Just the numbers would be the same. Whatever those two numbers are, they'd be exactly the same. Okay. So again, flux would be the same for both surfaces, but the field would be stronger at S1. Okay. Now let's talk about another example. Let's say I have a positive charge here. And again, it's going to make a field outward, okay, like so. And now this time I'm going to draw a cube around that. And the cube is going to be, the charge will be at the center of the cube. So I'll do the best I can to draw that. So here's my cube. And we're going to say that that charge is at the center of that cube. You need them. Now, I didn't quite draw it well enough, but that charge should be at the center of that cube. And my couple questions are, if I were going to use this equation to actually try to calculate the flux leaving that cube, it would be pretty difficult. If you look at any one particular face, so for instance, if I look at the right-hand face of this thing, right, the field varies both vertically and into the page along that face. So you would literally have to integrate twice, and you'd have to somehow figure out what the electric field strength is and the angle as a function of the angle and the distance away. And that would get really tricky, actually. That'd be a lot of math, okay? So I personally, I wouldn't do that. Now, for the spherical one, That's not so bad, right? Because all these field lines leave at a perpendicular to the surface, which is parallel to the surface vector. So for a sphere, it's pretty easy. For the cube, it would be much tougher to use this formula to actually calculate the flux. Okay, but I do hope that you would look at that and say, well, what if I drew a sphere around all this? Through which surface would more flux pass? Well, it'd still be the same, right? As just the 8 field lines are passing through both the cube and the sphere. Okay, so that's going to come into play in a little bit. All right, so how do I calculate that flux if I don't want to do this crazy math? Well, let me give you a couple examples. Let's say I have some positive charges. There's 1, there's 2, there's 3, and there's a 4th one. Okay, and each one's making a field. So I'm just going to draw 4 lines for each, make it real quick here. All right, and I asked you the following. Okay, so there's my 4 lines for each. Okay. I'm going to draw different spheres surrounding each of the charges. So let's say here's my first surface, symmetrically, the charge at the center. Okay. Let's say here's my second surface, the charge is not at the center. Let's say here's my third surface, the surface is bigger. And let's say here's my 4th surface. Okay, the charge is not in that surface. All right. And I asked you to figure out the net flux leaving each surface. Well, I hope that you would agree for surfaces 1, 2, and 3, the net flux leaving each surface would be identical. All 4 field lines leave each of those surfaces. So for these things, you would write, that the electric flux through 1 would equal the electric flux through 2 would equal the electric flux through 3, etc. Okay. What about this 4th one down here? All right, well, what's the net flux entering or leaving that surface? Well, I'm going to draw a few more field lines here just to kind of show you what's going on. I hope that you would agree that for every field line that enters the surface, the same field line leaves somewhere else. Enters there, leaves there. Enters there, leaves there. So what's the net electric flux leaving this surface? Well, it's going to be 0. So it turns out that the electric flux leaving a closed surface, that encloses a volume, has to do with the amount of charge that's inside that volume. All right. In these cases, you have a number. In this case, you don't. It's 0. Okay, because the charge is not in that last surface there. So let's go back to a sphere centered at the charge. Okay. So let's say here's our charge, and it's making a field. Now I'll draw some extra lines here. Okay, so there's our field leaving that charge. And let's say I've got a surface. All right, and that's a sphere that's centered, the charge is centered in that sphere. Well, the net electric flux leaving that closed volume would be the double integral closed surface of E dot dA. Now, thank goodness in this example, I don't have to do the integral because everywhere the field is perpendicular to the area or parallel to the area vector. So if that's like a dA right there, that little area is a dA, the field leaving that area is parallel to that dA. So there's no integration here. In other words, the field strength is the same everywhere along that sphere. Okay. So what is that field strength? Well, for a point charge, E is equal to K Q over R squared. Now I'm going to rewrite that in terms of epsilon naught. You might recall that K equals 1 over 4 pi epsilon naught. So E is equal to Q over 4 pi epsilon naught R squared. So these two equations are the same, okay? What's the area? So again, I don't have to do a dA anymore. I can just multiply by the area because the field's constant along everywhere along the area and parallel to the area vector everywhere along the area. Well, the area of a sphere is 4 pi R squared. So my net electric flux leaving that area is E, which is Q over 4 pi epsilon naught R squared times the area of that sphere, which is 4 pi R squared. And you'll notice that a lot of stuff cancels. The R squares go away and the 4 pi's go away. And you get a very simple answer. The net electric flux leaving that closed volume is simply equal to Q over epsilon naught. Okay. So you'll notice that that number, if I go back up to this example here, that number would be the same for 1, 2, and 3. I had the same amount of charge in each of those 3 spheres. It doesn't matter what the shape of the sphere, the area is at all. All that matters is how much charge do I got in there. The total flux leaving is just going to equal Q divided by that constant epsilon naught. For that fourth one, there is no charge inside the sphere, so the net flux is 0 because Q in is 0. So we're going to add one little thing to this. This would be Q in. Okay, that's the Q, the charge that's inside that surface. Okay. All right. So that leads us to Gauss's law. Okay, so we have 2 equations for electric flux, leaving a closed volume, a closed surface. We have this equation, and we have the general equation. If you put those 2 together, in other words, these 2 are measuring the same thing. So if I put those 2 together, you get Gauss's law. So this is Gauss's law. So Gauss figured out that if I do a closed surface, so double integral with the circle around it, which means a closed surface of E dot dA, that equals Q that's inside that volume, inside that surface, over epsilon naught. That is Gauss's law, and that is what we're going to be using throughout the rest of this unit, or rest of this chapter and the rest of the unit. All right, so the next video I'll do some minor examples with this, and then we'll continue on with some more complicated examples with this. I hope that video was helpful, and thank you very much.